In the first few 100,000 years after the Big Bang, the universe was not transparent. Space was filled everywhere with a hot, dense mixture of elementary particles, photons, electrons, protons, and light nuclei. Matter and radiation were not separate components evolving independently. They formed a single physical system, tightly coupled through electromagnetic interactions, behaving more like a fluid than a collection of individual particles. This state is known as the photon-baryon plasma. Photons dominated the energy density of the universe at this time. Their number exceeded that of baryons by roughly 1 billion to 1, and their pressure controlled the dynamics of the plasma. Baryons, mainly protons and helium nuclei, contributed most of the mass, but were dynamically subdominant. Free electrons, supplied by the fully ionized gas, played a crucial intermediary role. They provided the electric charges that allowed photons to interact efficiently with matter. As long as electrons remained unbound, radiation could not stream freely. Instead, photons scattered repeatedly, changing direction but not losing energy in the process. The dominant interaction responsible for this coupling was Thomson scattering. This process involves the elastic scattering of low-energy photons off free electrons. At the temperatures and photon energies present before recombination, Thomson scattering had a very large cross-section. The mean free path of a photon, the average distance it could travel before scattering, was extremely short, far smaller than any cosmological length scale. As a result, photons and baryons were locked together into a single tightly coupled fluid. This tight coupling regime imposed a collective behavior on the plasma. Radiation pressure resisted gravitational compression, while gravity attempted to pull matter into potential wells seeded by primordial density fluctuations. The competition between these effects generated acoustic oscillations, pressure-supported sound waves propagating through the plasma. These oscillations are central to the physics of the cosmic microwave background, but their detailed imprint appears primarily at smaller angular scales. At the largest scales, the key role of the tight coupling regime is different. It ensures that the radiation field remains extremely smooth, with only tiny temperature variations reflecting equally tiny perturbations in density and gravitational potential. As the universe expanded, it cooled. The temperature dropped steadily as wavelengths stretched with cosmic expansion. Eventually, conditions changed enough to alter the fundamental interaction between matter and radiation. This transition is known as recombination. Despite the name, recombination refers to the first stable combination of electrons and protons into neutral hydrogen atoms, not a repetition of an earlier process. Recombination occurred when the temperature fell to roughly 3,000 Kelvin, corresponding to an age of about 380,000 years. At this point, photons no longer had enough energy to keep hydrogen ionized efficiently. Electrons began binding to protons, forming neutral atoms. This process did not happen instantaneously. It unfolded over a finite redshift interval, governed by atomic physics, radiative transfer, and the expansion rate of the universe. The crucial physical consequence of recombination was a dramatic drop in opacity. Free electrons were the primary scatterers of photons. As electrons became bound into neutral atoms, the density of free electrons plummeted. Thomson scattering became ineffective. The mean free path of photons increased rapidly, growing from microscopic distances to cosmological scales in a short fraction of cosmic time. Radiation, previously trapped in the plasma, was suddenly able to propagate almost freely. This moment marks the decoupling of matter and radiation. Photons ceased to exchange momentum with baryons and began traveling along nearly unimpeded paths through expanding space. The radiation released at this time is what we now observe as the cosmic microwave background. It is important to understand that the cosmic microwave background does not originate from a single location. It originates from a surface in space-time. This surface is called the last scattering surface. It represents the set of points where photons last interacted significantly with matter before streaming freely toward us. Because the universe is expanding uniformly in all directions, the last scattering surface forms a spherical shell centered on the observer. Every direction we look corresponds to a different line of sight intersecting this shell at a different point. The cosmic microwave background is therefore a two-dimensional image of a three-dimensional event. It is a snapshot of the universe at the same cosmic time, projected onto the sky as a sphere. The thickness of the last scattering surface is finite but small compared to its radius. This thickness reflects the gradual nature of recombination. Some photons last scattered slightly earlier, some slightly later, but the spread in time is narrow enough that the surface can be treated, to high accuracy, as a thin shell. This geometric fact underlies the interpretation of the CMB as a two-dimensional field defined on the celestial sphere. The radiation released at decoupling possessed a remarkable property. It followed an almost perfect blackbody spectrum. A blackbody spectrum arises when radiation is in thermal equilibrium with matter, undergoing frequent interactions that redistribute energy among photons. Before recombination, the tight coupling between photons and electrons ensured precisely this condition. Any distortion in the spectrum was rapidly erased by scattering processes, driving the radiation toward equilibrium. As a result, when photons decoupled, they carried with them the spectral imprint of that equilibrium state. Subsequent cosmic expansion stretched their wavelengths, but preserved the shape of the spectrum. Today, the cosmic microwave background exhibits a blackbody spectrum corresponding to a temperature of about 2.7 Kelvin, with deviations constrained to be extraordinarily small. This is one of the strongest empirical confirmations of the hot Big Bang model. Despite this uniformity, the cosmic microwave background is not perfectly isotropic. Tiny temperature fluctuations exist at the level of 1 part in 100,000. These anisotropies are not random noise. They encode information about the physical conditions of the early universe and the seeds of all later structure. The small amplitude of these anisotropies has a physical origin. Density fluctuations in the early universe were extremely small. Inflationary models predict primordial perturbations with nearly scale-invariant spectra and amplitudes consistent with these observations. Gravitational potentials associated with these perturbations, slightly red-shifted or blue-shifted photons climbing out of or falling into them. Regions that were slightly denser or deeper in potential appeared marginally cooler or warmer in the radiation field. Temperature fluctuations in the cosmic microwave background therefore reflect variations in gravitational potential, density, and velocity at the surface of last scattering. On the largest angular scales, the dominant contribution comes from gravitational redshift effects, often described by the Sachs-Wolf mechanism. Photons emerging from deeper potential wells lose a small amount of energy, appearing cooler, while those emerging from shallower regions appear warmer. It is crucial to emphasize that these temperature fluctuations do not represent temperature differences in the ordinary thermodynamic sense. They do not indicate that one region of space was physically hotter than another by measurable macroscopic amounts. Instead, they represent fractional differences in photon energy arising from relativistic effects tied to space-time curvature and expansion. The cosmic microwave background is extraordinarily uniform in absolute terms. The angular scale of these fluctuations carries additional information. Large angular scales on the sky correspond to physical perturbations with wavelengths comparable to or larger than the horizon size at recombination. These modes had not yet undergone significant causal evolution by the time photons decoupled. They preserve information about the earliest conditions of the universe, including the initial spectrum of perturbations and any deviations from statistical isotropy. Smaller angular scales correspond to perturbations that were well within the horizon before recombination. These modes participated in acoustic oscillations, leading to the characteristic series of peaks observed in the angular power spectrum. Large angular scales, by contrast, are sensitive to global properties of space-time and initial conditions rather than microphysical processes. Because the cosmic microwave background provides only one realization of these largest modes, statistical uncertainty becomes unavoidable. This limitation, known as cosmic variance, is intrinsic and cannot be reduced by better instruments. It places a fundamental bound on how precisely large-scale features can be characterized. Nevertheless, the largest angular scales remain uniquely valuable because they probe physics inaccessible by any other means. The cosmic microwave background, then, is not merely ancient light, it is a physical record of a transition in the universe's history, frozen into a spherical shell that surrounds every observer. Its black-body spectrum testifies to an early phase of thermal equilibrium. Its tiny anisotropies encode information about primordial fluctuations, gravitational potentials, and the geometry of space-time itself. And its largest angular features offer a direct window into the earliest accessible moments of cosmic history, where the assumptions of isotropy and randomness can be tested against observation. The temperature variations observed in the cosmic microwave background form a field defined on the surface of the sky. At every direction, one can specify a temperature that differs slightly from the mean value. Mathematically, this is treated as a scalar function defined on a sphere. The sphere is not a physical object embedded in space, but a geometric representation of all possible lines of sight from the observer. Each point on this sphere corresponds to a direction in which photons last scattered at recombination. This temperature field is usually written as a fractional deviation from the mean temperature. Instead of working with absolute temperatures, cosmology focuses on relative fluctuations because the mean carries little information about structure. The resulting field is dimensionless and typically of order 1 part in 100,000. This formulation already reflects an important assumption, that the underlying signal is continuous and smooth across the sky, not a collection of discrete sources. To analyze such a field rigorously, one needs a mathematical basis appropriate for functions defined on a sphere. Ordinary Fourier modes, which are used for flat, infinite spaces, are not suitable. The natural analog on a sphere is provided by spherical harmonics. These functions form a complete, orthonormal set defined on the surface of a sphere. Any sufficiently smooth function on the sphere can be written as a sum of spherical harmonics with appropriate coefficients. The spherical harmonics are labelled by 2 integers, conventionally denoted L and M. The index L is a non-negative integer that sets the overall angular scale of the mode. The index M runs from -L to +L and distinguishes different patterns with the same angular scale but different orientations. For a given L, there are 2 L plus 1 independent modes corresponding to the different values of M. Expanding the temperature field in spherical harmonics separates the sky into contributions from different angular scales. Each coefficient in the expansion represents how strongly a particular harmonic contributes to the observed pattern. The full set of coefficients encodes all information contained in the temperature map, provided no information is lost through masking or smoothing. The multipole number L plays a central role in the interpretation of CMB data. Roughly speaking, L corresponds to an inverse angular scale. Low values of L describe features that vary slowly across the sky, spanning large angles. High values of EL describe rapidly varying features with small angular extent. A common approximation relates angular scale theta to L by the relation that theta is on the order of 180 degrees divided by L. This is not exact, but it provides useful intuition. Under this approximation, L equal to 2 corresponds to structures spanning most of the sky. L equal to 3 still probes very large angular scales. Values of L around a few hundred correspond to degree scale features. Values in the thousands probe arc-minute scale structure. This mapping connects mathematical abstraction directly to physical size at the surface of last scattering. Once the temperature field has been expanded in spherical harmonics, one can choose how to summarize the information contained in the coefficients. The most common summary is the angular power spectrum. The power spectrum is constructed by taking, for each L, the average of the squared magnitudes of the coefficients over all m. This yields a single number for each L, representing the typical amplitude of temperature fluctuations at that angular scale. The power spectrum discards information about orientation and relative phase between modes. It retains only the variance as a function of scale. This compression is justified under the assumption that the temperature field is a statistically isotropic Gaussian random field. In such a field, all statistical information is contained in the two-point correlation function, which is equivalent to the power spectrum. Higher-order correlations do not add independent information if the field is perfectly Gaussian. However, the spherical harmonic expansion contains more than just amplitudes. Each coefficient has a complex phase that encodes how different modes align relative to one another. These phases determine the actual spatial pattern on the sky. Two skies can have identical power spectra and yet look very different if their phase relationships differ. The power spectrum describes how much structure exists at each scale, but not how that structure is arranged. This distinction between power and phase becomes critical at low multipole numbers. At high L, where many modes contribute and statistical averaging is effective, phase information tends to wash out in visual impression. At low L, only a small number of modes exist. Their relative orientations and correlations can produce coherent, large-scale patterns that are visually and statistically distinctive. The lowest multipoles probe the largest angular scales, and therefore the largest physical scales accessible in the observable universe. These modes correspond to perturbations with wavelengths comparable to the diameter of the last scattering surface. Such perturbations were not shaped by local microphysical processes at recombination. Instead, they reflect the geometry and initial conditions of space-time itself. At these scales, the detailed physics of photon-baryon interactions becomes largely irrelevant. Acoustic oscillations, diffusion damping, and recombination kinetics primarily affect smaller scales. Large angular modes were outside the causal horizon for much of the early universe. They did not have time to oscillate or equilibrate. Their imprint in the CMB arises mainly through gravitational effects and projection geometry. This is why low L modes are often described as geometric rather than microphysical. They are sensitive to global properties. Curvature, topology, large-scale gravitational potentials, and the statistical properties of primordial perturbations. Any violation of statistical isotropy, any preferred direction, or any large-scale asymmetry is most likely to appear in these modes first. The dominance of geometry at low L also explains why anomalies at these scales are difficult to interpret. There is no detailed microphysical model to refine or adjust. One is probing boundary conditions rather than local dynamics. Small deviations from expectation cannot easily be attributed to poorly understood plasma physics. They raise questions about assumptions that are otherwise taken as foundational. A further complication arises from cosmic variance. Cosmic variance refers to the statistical uncertainty inherent in observing only a single realization of a random process. In the context of the cosmic microwave background, this means there is only one sky. One cannot observe multiple universes to build an ensemble average. The theoretical predictions describe the distribution from which skies are drawn, but observation provides only one draw. For each multipole L, cosmic variance imposes a minimum uncertainty on any estimate of power. This uncertainty scales inversely with the number of independent modes, which is 2L plus 1. At high L, this number is large, and cosmic variance becomes negligible compared to instrumental noise. At low L, the number of modes is small. For L equal to 2, there are only 5 modes. For L equal to 3, there are 7. As a result, the fractional uncertainty due to cosmic variance at low ELL is enormous. Even a perfectly noiseless experiment would be unable to determine the true underlying power at these scales with high precision. This uncertainty is not a technical limitation. It is a fundamental property of inference in a finite universe. Cosmic variance affects not only power estimates, but also any statistic derived from low-L modes. Alignments, phase correlations, and directional asymmetries are all subject to large statistical fluctuations. This does not make such features meaningless, but it complicates the assessment of their significance. One must distinguish between unlikely but permissible realizations and genuine evidence for new physics. The fact that only one sky exists also introduces subtle methodological issues. Many statistical tests are devised after features are noticed in the data. This a posteriori selection inflates apparent significance. When one inspects a single realization closely enough, some unusual pattern is almost guaranteed to appear. The challenge is determining whether the observed pattern is more unlikely than expected, given the freedom to look for patterns in many ways. At high multipoles, the large number of modes allows rigorous statistical averaging. The distribution of power becomes sharply peaked, and deviations from expectation are easily quantified. At low multipoles, the distribution is broad. Rare realizations are not strongly suppressed. This makes low-L anomalies intrinsically ambiguous. Despite these limitations, the mathematical framework remains essential. The spherical harmonic decomposition provides a precise language for describing the temperature field. It cleanly separates scale, orientation, amplitude, and phase. It allows predictions to be tested quantitatively and anomalies to be defined unambiguously. The cosmic microwave background is therefore not analysed as an image in the usual sense, but as a set of coefficients drawn from a probabilistic distribution. Geometry, statistics, and physics are intertwined in this representation. The largest scales probe assumptions that are otherwise difficult to access, while the smallest scales test detailed physical models with high precision. Within this framework, any unexpected correlation among low multipoles acquires significance beyond its numerical amplitude. It is not merely a deviation in power, it represents a deviation in the structure of the temperature field itself. Understanding such deviations requires careful attention to the mathematics of the sphere, the limits imposed by cosmic variance, and the unavoidable fact that the universe offers only a single sky to observe. Modern cosmology is built on a small set of foundational assumptions about the large-scale structure of the universe. Among the most important of these are homogeneity and isotropy. Homogeneity asserts that, when viewed on sufficiently large scales, the universe is statistically the same at every location. Isotropy asserts that it is statistically the same in every direction. Together, these assumptions form the cosmological principle. They are not exact statements about local structure, but probabilistic statements about averages taken over scales far larger than galaxies, clusters, or even superclusters. In the context of the lambda-CDM model, these assumptions are elevated from philosophical starting points to quantitative hypotheses. They are embedded directly into the mathematical description of space-time, the evolution of perturbations, and the interpretation of observational data. The Friedman-Lemaitre-Robertson-Walker metric, which underlies standard cosmology, is constructed to be exactly homogeneous and isotropic at the background level. All deviations from uniformity are treated as perturbations superimposed on this symmetric background. This distinction is crucial. Homogeneity and isotropy do not imply that the universe is smooth everywhere. They imply that the statistical properties of fluctuations are invariant under translations and rotations. A universe can contain complex structure and still satisfy satisfy the cosmological principle, provided that no location or direction is preferred when averaged over sufficiently large volumes. Within this framework, the temperature fluctuations of the cosmic microwave background are modelled as realizations of a statistically homogeneous and isotropic random field. This assumption has precise mathematical consequences. It constrains how fluctuations are distributed, how they correlate with one another, and how their statistical moments behave. One of the central predictions of lambda CDM is that the primordial perturbations that seed cosmic structure form a Gaussian random field. This prediction arises naturally from the simplest models of inflation, in which quantum fluctuations of a single scalar field are stretched to cosmological scales. In these scenarios, the fluctuations originate as vacuum fluctuations with nearly Gaussian statistics. Non-Gaussianities are possible, but they are expected to be small and tightly constrained. A Gaussian random field is fully characterized by its two-point correlation function. All higher-order correlations can be expressed in terms of this function. In practical terms, this means that once the angular power spectrum of the cosmic microwave background is specified, no additional statistical information should remain in the temperature field apart from random realization noise. An immediate consequence of Gaussianity is the expectation of random phases. When the temperature field is expanded in spherical harmonics, each coefficient has an amplitude and a phase. Gaussianity implies that the phases of different modes are independent and uniformly distributed. There should be no preferred alignment or correlation among phases beyond what is expected from chance. Random phases ensure that, although power may vary with angular scale, the spatial arrangement of hot and cold regions lacks coherent global structure. Patterns such as alignments, planar features, or axes extending across the sky are statistically disfavored. They can occur in individual realizations, but only with probabilities that can be calculated within the model. Statistical isotropy further constrains the form of correlations. Isotropy means that the statistical properties of the field are invariant under rotations. Rotating the sky by any angle should not change the probability distribution of temperature fluctuations. This symmetry has concrete implications for the covariance of spherical harmonic coefficients. Under statistical isotropy, coefficients with different values of EL or EM are uncorrelated. The variance of each coefficient depends only on L, not on M. This is why the angular power spectrum is indexed solely by L. Any dependence on M would signal a preferred direction or a breaking of rotational invariance. Rotational invariance also implies that all orientations of a given multipole pattern are equally likely. A quadrupole aligned with any particular axis should be no more probable than one aligned with any other. The orientation of large-scale features should therefore carry no cosmological information. Only their amplitude as a function of scale should matter. From this perspective, the sky should not single out any special direction. There should be no axis embedded in the temperature field that carries statistical significance. Any apparent alignment with physically defined directions, such as the plane of the solar system or the motion of the observer, should be attributable to chance, contamination, or systematic error rather than fundamental physics. Inflation plays a central role in enforcing these expectations. In standard inflationary models, the rapid exponential expansion smooths out pre-existing anisotropies and inhomogeneities. Any initial directional dependence in the metric or matter content is diluted to negligible levels. By the time inflation ends, the universe is predicted to be extraordinarily isotropic on large scales. At the same time, inflation generates perturbations through quantum fluctuations that are nearly scale invariant and statistically homogeneous and isotropic. The mechanism does not imprint a preferred direction. The expansion is locally the same in all directions, and the underlying quantum vacuum respects rotational symmetry. As a result, the perturbations inherit this symmetry. This inflationary smoothing is not merely qualitative. Quantitative bounds exist on the level of anisotropy that could survive inflation without conflicting with observations. These bounds are extremely tight. Any residual large-scale anisotropy would need to be finely tuned or supported by non-standard physics to remain observable today. Statistical isotropy has a precise mathematical definition. A random field defined on the sphere is statistically isotropic if its statistical moments are invariant under the action of the rotation group. In practice, this means that correlation functions depend only on angular separation, not on absolute position or orientation. The two-point correlation function of the temperature field provides a clear example. Under isotropy, the correlation between temperatures in two directions depends only on the angle between those directions. It does not depend on where the pair lies on the sky. This rotational invariance ensures that the correlation function can be expanded in Legendre polynomials, leading directly to the angular power spectrum. In harmonic space, statistical isotropy manifests as diagonal covariance, the expectation value of the product of two spherical harmonic coefficients is 0 unless they share the same L and M. Any off-diagonal correlation would indicate a violation of isotropy. This provides a powerful diagnostic for testing the assumption. Testing statistical isotropy observationally is therefore a matter of searching for deviations from these predictions. One approach is to look for anisotropies in the angular power spectrum itself. If power depends on M or varies systematically across the sky, isotropy may be violated. Another approach examines higher-order statistics that are sensitive to phase correlations and directional dependence. Hemispherical asymmetries offer a simple test. One can divide the sky into hemispheres along various axes and compare the variance or power between them. Under isotropy, differences should be consistent with statistical fluctuations. Persistent or extreme asymmetries may signal a breakdown of the assumption. More sophisticated methods involve bipolar spherical harmonics, which generalize the standard harmonic expansion to allow explicit modeling of anisotropic correlations. These techniques can detect subtle departures from rotational invariance and quantify their amplitude and scale dependence. Polarization provides an independent avenue for testing isotropy. The polarization pattern of the cosmic microwave background is generated by the same physical processes as temperature anisotropies, but encodes different combinations of perturbations. Consistency between temperature and polarization anisotropy statistics strengthens the case for isotropy. Discrepancies may point to new physics or unaccounted systematics. Large-scale structure surveys also offer complementary tests. If primordial perturbations were anisotropic, their imprint should persist in the distribution of galaxies and matter at late times. Cross-correlating cosmic microwave background anomalies with large-scale structure can therefore test whether observed features originate from the early universe or from local effects. Despite extensive testing, the lambda CDM model with statistically isotropic initial conditions has been remarkably successful. Most observables agree with its predictions to high precision. Deviations, when reported, tend to appear at the largest angular scales, where cosmic variance is dominant and statistical power is weakest. This creates a tension that is methodological rather than purely empirical. The largest scales are the most sensitive to violations of isotropy, but they are also the least statistically robust. Interpreting anomalies at these scales requires careful consideration of selection effects, foreground contamination, and the limits imposed by observing a single realization. Nevertheless, statistical isotropy remains a falsifiable hypothesis. It is not assumed by fiat. It is tested continuously as new data and methods become available. Any confirmed violation would have profound implications for our understanding of the early universe, the mechanism of inflation, and the fundamental symmetries of spacetime. Within lambda CDM, however, the expectation is clear. The universe should have no preferred directions on the largest scales. Temperature fluctuations should form a Gaussian random field with random phases, rotationally invariant statistics, and correlations that depend only on scale. Any apparent axis, alignment, or directional dependence must therefore be treated as a potential anomaly, requiring explanation either as a rare statistical fluctuation or as evidence that one of the model's core assumptions is incomplete. The first direct observational window onto the large-scale anisotropy of the cosmic microwave background came from the COBE satellite. Launched in 1989, COBE was not designed to produce detailed maps of small-scale structure. Its primary goal was more fundamental, to determine whether the cosmic microwave background possessed the tiny temperature fluctuations predicted by structure formation models at all. At the time, this was not yet observationally established. Upper limits existed, but no unambiguous detection. COBE carried 3 main instruments, but the one relevant for anisotropy measurements was the differential microwave radiometer. This instrument compared the temperature of the sky in pairs of directions separated by a fixed angle rather than measuring absolute temperatures. This differential approach was essential for suppressing instrumental drifts and systematic offsets, but it imposed important limitations on angular resolution and map reconstruction. The effective angular resolution of the COBE anisotropy maps was about 7 degrees. This corresponds to very low multipole numbers. In harmonic space, COBE was primarily sensitive to multipoles roughly below L, approximately 20, with meaningful signal-to-noise concentrated at even lower values. Structures on degree scales or smaller were completely inaccessible. As a result, COBE probed only the largest angular features of the sky, precisely the regime where cosmic variance dominates and where interpretation is most subtle. Despite these limitations, the detection achieved by COBE was historic. In 1992, temperature anisotropies at the level of tens of microkelvin were reported. This confirmed a key prediction of the hot Big Bang model and provided the first direct evidence of primordial density perturbations. The observed amplitude was consistent with what was required to seed the formation of galaxies and large-scale structure. The earliest analyses focused almost entirely on the angular power spectrum. Given the coarse resolution and limited number of modes accessible, this was a natural choice. The power spectrum provided a simple, rotationally invariant summary of the data, well aligned with theoretical expectations and statistical assumptions. At the time, the primary question was whether the amplitude and scale dependence of fluctuations were broadly consistent with inflationary models. Within this framework, one feature stood out early on. The quadrupole amplitude appeared low. The quadrupole, corresponding to L equals 2, represents the largest scale variation across the sky. In the COBE data, its measured power was smaller than the mean value predicted by standard cold, dark matter models normalized to smaller scale structure. This discrepancy was not dramatic, but it was persistent. The low quadrupole amplitude raised early concerns about large-scale power in the cosmic microwave background. Some analyses suggested that the power spectrum at the lowest multipoles was suppressed relative to expectations. Others argued that the discrepancy was well within cosmic variance and should not be overinterpreted. At the time, the statistical framework for assessing such deviations was still evolving, and the number of independent modes was extremely small. It is important to emphasize how limited the data were. For the quadrupole, there are only 5 independent modes in a full sky measurement. COBE's noise levels, sky coverage limitations, and foreground subtraction uncertainties further reduce the effective information content. The resulting uncertainty on the quadrupole power was large. Even a factor of 2 deviation from the theoretical mean was not especially unlikely. As a result, the low quadrupole was generally treated with caution. It was noted, discussed, and included in parameter fits, but it was not regarded as a serious challenge to the standard model. Attention was focused instead on the overall normalization of fluctuations and the confirmation of near-scale invariance across the accessible range of multipoles. Another key limitation of the early COBE analyses was the near-total absence of phase-based investigations. The temperature field was decomposed into spherical harmonics, but almost all published results marginalized over the phases by construction. This was not an oversight so much as a reflection of priorities and assumptions. At the time, the working hypothesis was that the temperature field was a statistically isotropic Gaussian random field. Under this assumption, the phases of spherical harmonic coefficients carry no cosmological information. They are expected to be uniformly random. Any particular realization, including one with visually striking patterns, is statistically equivalent to any other realization with the same power spectrum. Given this expectation, analyzing phases was not viewed as a meaningful test. Furthermore, with such low angular resolution, the visual appearance of the sky was dominated by a handful of modes. Apparent alignments or patterns could easily arise by chance. Without a clear theoretical motivation or a robust statistical framework, phase correlations were considered an unreliable basis for inference. Foreground contamination further complicated matters. Galactic emission, particularly from synchrotron radiation and thermal dust, dominates the microwave sky at low frequencies and large angular scales. Although COBE observed at multiple frequencies, component separation techniques were relatively primitive by modern standards. Residual foreground contamination was a serious concern, especially at low multipoles where galactic emission is strongest. This reinforced the emphasis on conservative, rotationally invariant statistics. By averaging over m for each L, one reduced sensitivity to localized or directional contamination. Phase information, by contrast, is highly sensitive to foreground residuals and sky cuts. In the early 1990s, this sensitivity was viewed as a liability rather than an opportunity. As a result, the early COBE legacy was framed almost entirely in terms of power. The main conclusions were that anisotropies existed, that their amplitude was small, and that their scale dependence was broadly consistent with inflationary expectations. The low quadrupole was acknowledged, but largely set aside as a curiosity rather than a crisis. Only later, after higher resolution data became available, did researchers return to the COBE maps with new questions. When WMAP and later Planck revealed unexpected alignments and phase correlations at low multipoles, the natural question arose: were these features already present in the COBE data, hidden by limited resolution and early analysis choices? Retrospective reanalyses of COBE maps were therefore undertaken. Using improved foreground models, refined statistical tools, and a focus on phase information, researchers revisited the original data. What they found was subtle, but intriguing. Within the large uncertainties, the quadrupoles and octopole patterns inferred from COBE appeared broadly consistent with those seen later by WMAP. The alignments were not sharp or unambiguous in the COBE data alone. The noise level and beam smoothing significantly blurred the patterns. However, the orientations of the largest scale modes did not contradict later findings. This suggested that the anomalies were not artifacts introduced by newer instruments or data processing pipelines, but might reflect genuine features of the sky. At the same time, these reanalyses highlighted the limitations of COBE with renewed clarity. Small changes in foreground modelling or map-making assumptions could noticeably alter the inferred low-L patterns. The statistical significance of any alignment extracted from COBE alone remained weak. No firm conclusions could be drawn without higher quality data. Nevertheless, the historical role of COBE became more nuanced. It was no longer viewed solely as the experiment that confirmed anisotropies, but also as the first dataset to hint, however faintly, at potential irregularities on the largest angular scales. These hints were not recognized at the time because the conceptual framework to interpret them did not yet exist. In retrospect, this is not surprising. The anomalies associated with the so-called axis of evil are subtle deviations from statistical expectations, not gross violations. Detecting them requires not only high-quality data, but also a willingness to question assumptions that had been extraordinarily successful elsewhere. In the early 1990s, the priority was to establish the existence of anisotropies, not to scrutinize their detailed geometry. COBE thus occupies a foundational but ambiguous position in the story. It provided the first glimpse of the large-scale microwave sky, revealed a low quadrupole that would later attract renewed attention, and set the stage for more detailed investigations. At the same time, its limitations ensured that any deeper anomalies remained just below the threshold of significance. The early concerns about large-scale power did not overturn the emerging consensus, but they planted seeds of doubt that would resurface with better data. The decision to ignore phase information was methodologically sound given the context, yet it delayed recognition of patterns that might have been present all along. When later missions revisited the same scales with sharper eyes, the question was no longer whether anomalies existed, but whether they had been quietly imprinted on the sky since the very beginning of observational cosmology. The launch of the WMAP satellite marked a decisive shift in the study of cosmic microwave background anisotropies. Unlike COBE, which had been optimized for detection rather than precision mapping, WMAP was designed from the outset to produce full sky maps with substantially higher angular resolution, lower noise, and improved control of systematics. Its observational strategy, frequency coverage, and scanning pattern were all chosen to enable detailed statistical tests of the standard cosmological model across a wide range of angular scales. The effective angular resolution of WMAP was approximately 0.2 degrees in its highest frequency channels, more than an order of magnitude improvement over COBE. This increase opened access to multipoles extending into the hundreds, allowing acoustic peaks to be resolved clearly for the first time in a full-sky dataset. At the same time, WMAP retained nearly complete sky coverage, observing over 80% of the celestial sphere even after conservative galactic masks were applied. This combination of resolution and coverage was crucial. It enabled small-scale physics to be studied with precision while preserving sensitivity to the largest angular modes where global properties of the universe are encoded. From the perspective of low multipoles, WMAP represented not just a refinement, but a qualitative leap. Noise levels at EL equals 2 and L equals 3 were dramatically reduced. Beam effects were better characterized. Foreground separation benefited from 5 frequency bands spanning a wide range of microwave wavelengths. For the first time, the quadrupole and octopole could be examined not merely as amplitudes in a power spectrum, but as concrete spatial patterns on the sky with well-defined orientations. It was within this context that attention began to shift from power alone to the geometry of the low L modes. When researchers visualized the reconstructed quadrupole and octopole temperature patterns from WMAP data, they noticed something unexpected. The hot and cold regions associated with these two lowest multipoles appeared not to be randomly oriented with respect to one another. Instead, they exhibited a striking degree of alignment. The quadrupole pattern, corresponding to EL equals 2, can be visualized as a distribution with 2 hot and 2 cold lobes across the sky. The octopole, EL equals 3, produces a more complex pattern with additional lobes. Under statistical isotropy and Gaussian initial conditions, the relative orientation of these patterns should be random. There is no physical reason within lambda CDM for the principal axes of different multipoles to coincide. In the WMAP maps, however, the quadrupole and octopole appeared to share a common axis. Their dominant features lay in nearly the same plane, and their extrema clustered along similar great circles. Quantitative analyses confirmed that this impression was not merely subjective. Measures of alignment based on multipole vectors, angular momentum dispersion, and other statistics indicated that the probability of such close alignment arising by chance was low, though not vanishingly so. To make this notion precise, researchers introduced methods for defining preferred axes associated with individual multipoles. One approach involved constructing vectors that characterize the orientation of a multipole's pattern on the sky. These vectors are derived from the spherical harmonic coefficients in a way that isolates directional information while remaining insensitive to overall amplitude. For each multipole, one can define an axis that maximizes certain rotationally invariant quantities, such as angular momentum dispersion. Intuitively, this axis corresponds to the direction about which the temperature pattern varies most strongly. In a statistically isotropic universe, the axes defined for different multipoles should be randomly oriented with respect to one another. In the WMAP data, the axes associated with ALL equals 2 and L equals 3 were found to be unusually close. The angle between them was much smaller than typical values obtained in simulations of isotropic Gaussian skies. This proximity was robust across different foreground cleaned maps and persisted under variations in analysis technique. Closely related to this observation was the discovery of planarity in the low multipoles. Planarity refers to the tendency of a multipole's power to be concentrated in modes with high m values when expressed in a particular coordinate system. Physically, this corresponds to temperature variations that are preferentially confined to a plane, producing band-like structures rather than fully three-dimensional patterns. Both the quadrupole and octopole in the WMAP maps exhibited an unusual degree of planarity. When rotated into their respective preferred frames, a large fraction of their power resided in a single plane. This was again unexpected under the assumption of random phases and rotational invariance. While planarity can occur by chance for individual multipoles, its simultaneous appearance in both ELL equals 2 and L equals 3, aligned along nearly the same plane, was statistically disfavored. Another way to characterize these features involved examining angular momentum vectors associated with the multipoles. For each multipole, one can compute vectors related to the flow of power across the sphere, analogous to angular momentum in quantum mechanics. These vectors provide a compact representation of the multipole's orientation. Analyses showed that the angular momentum vectors of the quadrupole and octopole were not only individually well defined, but also strongly correlated with each other, their directions clustered within a small region of the sky. This correlation was quantified using Monte Carlo simulations, which demonstrated that such close alignment occurred infrequently in random realizations drawn from isotropic models. What made these findings especially striking was their coherence across different statistical descriptions. Whether one examined multipole vectors, angular momentum dispersion, or planarity measures, the conclusion was similar. The lowest multipoles were not behaving independently. They appeared to define a common geometric structure on the sky. This coherence led naturally to the notion of an unexpected collinearity at the largest angular scales. Instead of each multipole selecting its own random orientation, the quadrupole and octopole seemed to know about each other's directions. In the language of statistical isotropy, this represents a coupling between modes that should be independent. The situation became even more provocative when the orientation of this common axis was compared to physically meaningful directions defined by the observer's environment. The preferred axis identified from the quadrupole-octopole alignment was found to lie close to the plane of the ecliptic, the plane defined by Earth's orbit around the Sun. It was also not far from the direction of the solar system's motion with respect to the cosmic microwave background dipole. This coincidence immediately raised concerns about non-cosmological explanations. The ecliptic plane has no significance in standard cosmology. It is a purely local feature associated with the geometry of the solar system. Any correlation between the cosmic microwave background and the ecliptic therefore suggests either a remarkable coincidence or some form of contamination or systematic effect tied to the observing platform or data processing. The proximity of the alignment axis to the ecliptic was quantified in several studies. Depending on the precise definition of the axis and the map used, the angular separation ranged from a few degrees to a few tens of degrees. While not exact, this proximity was close enough to attract serious attention, particularly given the absence of any known cosmological mechanism that would single out the ecliptic. At the same time, the alignment did not coincide perfectly with any single obvious local direction. It was not exactly aligned with the dipole, nor exactly perpendicular to the galactic plane. This ambiguity complicated attempts to attribute the effect to a simple systematic error. Instrumental artifacts often leave signatures aligned with scan patterns or coordinate grids. The observed axis did not match these patterns cleanly. As discussion of these anomalies intensified, a memorable label emerged. In a 2005 paper by Land and Magejo, the term axis of evil was introduced to describe the apparent alignment of the lowest multipoles. The phrase was intentionally provocative, echoing political language of the time, but it served a practical purpose. It provided a concise way to refer to a collection of related anomalies involving preferred directions, planarity, and low L correlations. The name captured the unease felt by many cosmologists. The standard model of cosmology had been spectacularly successful in explaining a wide range of observations, yet here was a feature that seemed to resist easy categorization. It was not a gross inconsistency, but a subtle pattern that challenged deeply held assumptions about randomness and isotropy. Importantly, the introduction of the term did not imply a consensus about interpretation. Some researchers viewed the alignment as a statistical fluke, amplified by a posteriori selection and the human tendency to see patterns. Others regarded it as a potential clue to new physics or unrecognized systematics. The debate was vigorous and often contentious. What was clear, however, was that WMAP had changed the conversation. The improved resolution and sky coverage transformed low L anomalies from vague hints into concrete analyzable features. Phase information, long neglected, became central. Orientation, once assumed irrelevant, was now scrutinized carefully. The discovery of the quadrupole octopole alignment did not overturn lambda CDM, but it exposed a region of parameter space where the model's assumptions were being tested at their limits. It highlighted the tension between theoretical expectations of statistical isotropy and the empirical reality of a single observed sky. In this sense, the axis of evil was not just a curiosity, it was a stress test. It forced cosmologists to confront the fact that their most fundamental assumptions were probabilistic, not absolute. It underscored the difficulty of interpreting large-scale features in a universe where cosmic variance is unavoidable. Whether the alignment represents new physics, subtle contamination, or an improbable but permissible realization remains an open question. What WMAP established beyond doubt is that the largest scales of the cosmic microwave background are rich with structure that cannot be fully captured by the power spectrum alone. Geometry, orientation, and correlation matter. And once these features were revealed, they could no longer be ignored. When the low multipole anomalies of the cosmic microwave background are examined carefully, it becomes clear that their defining feature is geometric rather than energetic. The anomaly does not primarily concern how much power exists at large angular scales, but how that power is arranged on the sky. This distinction is fundamental. A deficit or excess of power can be described entirely by the angular power spectrum. A geometric anomaly cannot. In a statistically isotropic Gaussian random field, power and geometry are largely decoupled. The power spectrum specifies the variance of fluctuations at each angular scale, while the phases of the spherical harmonic coefficients determine how those fluctuations are spatially distributed. Under the assumptions of lambda CDM, the phases are random. As a result, Geometry carries no additional information beyond chance realization. Any large-scale pattern that appears visually striking is expected to be statistically equivalent to any other pattern with the same power spectrum. The axis of evil departs from this expectation in a specific way. The anomaly is not that the quadrupole or octopole amplitudes are unusual by themselves, although the quadrupole is indeed low. Rather, it is that the spatial patterns associated with these multipoles exhibit correlated structure. Their phases are not behaving as independent, random variables. Instead, they appear to conspire to produce a coherent orientation. This distinction between phase correlations and power anomalies is essential. A power anomaly refers to the magnitude of fluctuations at a given multipole deviating from the ensemble mean. Such deviations are expected to occur occasionally because of cosmic variance. Phase correlations, by contrast, refer to relationships among the orientations and shapes of modes. These are far less likely to arise by chance, especially when they involve multiple independent multipoles. The quadrupole and octopole each possess their own set of phases. Under Gaussianity, these phases should be uniformly distributed and uncorrelated. The probability that two such low-order multipoles would independently select nearly the same orientation is small, but not impossible. What makes the situation more striking is that this alignment is accompanied by additional geometric features, notably planarity. Planarity, in this context, refers to the tendency of a multipole's temperature variation to be concentrated in a single plane. Physically, a planar multipole produces temperature extrema that lie along a great circle on the sky, rather than being distributed more isotropically. When expressed in spherical harmonics, this corresponds to power being concentrated in modes with large absolute values of m in an appropriately chosen coordinate system. To understand why this is unusual, it is helpful to recall that the decomposition into M modes depends on the choice of coordinate axes. For a random isotropic field, no particular orientation should maximize the contribution of high M modes. One expects the power to be distributed roughly evenly among M values when averaged over realizations. A highly planar multipole, however, selects a preferred axis about which its structure is organized. In the observed sky, both the quadrupole and the octopole exhibit an unusually high degree of planarity when rotated into their respective preferred frames. Moreover, these preferred frames are nearly the same. This means that the two lowest multipoles are not only planar, but planar in the same direction. This shared geometry is a key component of the anomaly. Visualization plays an important role in appreciating this behavior. When the low L modes are reconstructed individually and plotted on the sky, the quadrupole and octopole can be viewed as smooth temperature patterns with only a few extrema. Unlike high L modes, which appear noisy and irregular, these large-scale modes are simple and highly structured. In such visualizations, the quadrupole often appears as a band of alternating hot and cold regions encircling the sky, while the octopole adds additional structure along a similar plane. When these maps are overlaid or compared, the alignment becomes evident even to the eye. While visual impressions are not sufficient for statistical claims, they motivate quantitative analysis. To assess whether such patterns are unusual, they must be compared against ensembles of simulated skies generated under the assumptions of lambda CDM. These Gaussian simulations reproduce the observed power spectrum but assign random phases to each mode. By generating large numbers of such realizations, one can construct probability distributions for alignment measures, planarity statistics, and angular separations. In these simulations, it is common to find individual multipoles that are planar or that align with another multipole to some degree. What is rare is the simultaneous occurrence of strong planarity in both L equals 2 and L equals 3, combined with a small angular separation between their preferred axes. The observed sky lies in the tail of the distribution for several independent geometric statistics. Angular separation statistics provide a concise way to quantify alignment. One can define a vector characterizing the orientation of each multipole, then compute the angle between these vectors. For random orientations, the probability distribution of this angle is uniform in cosine. Small angles are therefore suppressed by simple geometry. When the observed separation is compared to this distribution, it appears unusually small. Importantly, these conclusions depend on how the orientation vectors are defined. Different constructions emphasize different aspects of the multipole geometry. Some definitions focus on angular momentum dispersion, others on multipole vectors or extremer clustering. While the numerical values of alignment significance vary across methods, the qualitative result is robust. The lowest multipoles appear more aligned than expected under isotropy. This robustness across definitions is one reason the geometric anomaly has attracted sustained attention. A low quadrupole amplitude alone is not particularly surprising. Cosmic variance allows for substantial scatter at L equals 2. Indeed, a low quadrupole had already been noted in COBE data without provoking major concern. Alignment, however, introduces a qualitatively different issue. It implies correlation where independence is expected. The alignment is therefore more surprising than the low power because it challenges the assumption of random phases. Low power can be accommodated by statistical fluctuation. Correlated geometry across multipoles is harder to dismiss, particularly when it involves the largest scales that probe initial conditions directly. Another subtle aspect of the anomaly concerns its dependence on coordinate choice. Because spherical harmonic coefficients depend on the chosen coordinate system, one must ensure that any detected alignment is not an artifact of analysis in a particular frame. Robust studies therefore search over rotations of the sky to identify preferred frames intrinsic to the data rather than imposing them a priori. When this is done, the preferred axes emerge from the data themselves. They are not tied to galactic coordinates by construction. Nevertheless, once identified, they can be compared to known physical planes and directions. It is in this comparison that the proximity to the ecliptic plane becomes apparent. At the same time, the fact that planarity and alignment are revealed only after searching over orientations introduces a statistical subtlety. The act of searching for the most planar frame or the smallest angular separation effectively increases the number of trials. This must be accounted for when assessing significance. Failure to do so can exaggerate the improbability of the observed configuration. Even when such corrections are applied, however, the anomaly does not disappear entirely. Its statistical weight diminishes, but the qualitative deviation from expectation remains. This persistence across coordinate systems and statistical treatments suggests that the effect is not a trivial artifact of representation. The geometric character of the anomaly thus lies at the intersection of phase information orientation statistics and global symmetry. It is not a feature of any single multipole, nor of any single statistic. It is a pattern that emerges only when the lowest modes are considered together as geometric objects embedded on the sphere. This is precisely what makes the axis of evil difficult to interpret. It is neither a sharp violation of lambda CDM nor an easily dismissed fluctuation. It occupies a grey zone where geometry matters, statistics are weak, and theoretical guidance is limited. Understanding it requires moving beyond power spectra and engaging directly with the spatial structure of the largest scale fluctuations in the universe. Assessing the statistical significance of the axis of evil requires a careful examination of how probability is defined, how hypotheses are framed, and how data are interrogated. Unlike small-scale features of the cosmic microwave background, where well-defined pipelines and established likelihood functions dominate the analysis, large-scale anomalies exist in a regime where statistical inference is intrinsically fragile. The difficulty does not arise from lack of sophistication, but from fundamental limitations imposed by geometry, cosmic variance, and the uniqueness of the observed sky. At the core of nearly all significance estimates lies Monte Carlo sky generation. This technique provides the bridge between theoretical expectation and observational realization. In practice, one generates a large ensemble of simulated skies drawn from the lambda CDM model, with parameters fixed to best fit values derived from observations. Each simulated sky represents a possible universe consistent with the model's assumptions, statistical isotropy, Gaussianity, and a specified angular power spectrum. The generation process begins in harmonic space. For each multipole L and azimuthal index M, spherical harmonic coefficients are drawn from complex Gaussian distributions with variances set by the theoretical power spectrum. These coefficients are statistically independent except for the constraint imposed by reality of the temperature field. Once generated, the coefficients are transformed back into real space temperature maps, optionally smoothed, masked, or processed in the same way as the observational data. This ensures that simulations and data are treated symmetrically. By repeating this procedure many thousands or millions of times, one constructs an empirical distribution for any statistic of interest. The observed value of that statistic can then be compared to the distribution to assess how typical or atypical it is under the assumed model. This approach is conceptually straightforward, but its validity depends critically on the definition of the null hypothesis. The null hypothesis in this context is usually that the cosmic microwave background temperature field is a statistically isotropic Gaussian random field consistent with lambda CDM. This hypothesis specifies not just the power spectrum, but the full probability distribution of the spherical harmonic coefficients. It asserts that phases are random, that different multipoles are uncorrelated, and that no direction in space is preferred. Importantly, the null hypothesis does not assert that every realization will look isotropic by eye. It allows for chance alignments, power deficits, and unusual-looking patterns. The question is not whether an anomaly exists, but whether it is sufficiently improbable under the null to warrant rejecting or modifying the model. Defining the null hypothesis precisely is more subtle than it may appear. Choices must be made about which parameters are fixed and which are allowed to vary. For example, one may generate simulations using the best fit power spectrum derived from the same data being tested. Alternatively, one may use a theoretically motivated spectrum independent of the low-L anomalies. Each choice carries implications for interpretation, particularly when anomalies themselves influence parameter estimation. Once the null hypothesis is specified, the next step is the choice of test statistics. A test statistic is a numerical quantity designed to capture the feature of interest. In the case of the axis of evil, many such statistics have been proposed. These include measures of angular separation between multipole axes, planarity estimators, angular momentum dispersion metrics, multipole vector alignments, extrema clustering, and various combinations thereof. Each statistic emphasizes a different aspect of the geometry. Some are sensitive primarily to orientation, others to shape, others to correlations between multipoles. None is uniquely privileged by theory. This freedom is both a strength and a weakness. It allows researchers to probe different facets of the data, but it also opens the door to selection effects. In an ideal hypothesis test, the statistic would be defined before examining the data, motivated by a clear theoretical prediction. In practice, many axis of evil statistics were devised after intriguing patterns were noticed in the observed sky. This introduces a posteriori selection bias. The statistic is chosen because it highlights an apparent anomaly, not because it was uniquely predicted by the model. A posteriori selection bias inflates significance estimates by effectively conditioning on the presence of an unusual feature. If one looks at a single realization of a random field and invents a statistic tailored to what one sees, the resulting p-value no longer reflects the probability of that feature arising under the null. It reflects the probability of that feature arising given that one looked for it in that particular way. Closely related to this issue is the look elsewhere effect. This effect arises whenever multiple tests are performed on the same data. Even if each individual test has a low probability of producing an extreme result under the null hypothesis, the probability that at least one test will do so increases with the number of tests performed. In the context of the axis of evil, the look elsewhere effect manifests in several ways. Researchers examine multiple multipoles, multiple definitions of axes, multiple alignment measures, and multiple coordinate systems. They may test alignments with various physically defined directions, such as the galactic plane, the ecliptic, or the dipole direction. Each additional comparison increases the effective number of trials. Correcting for the look elsewhere effect requires careful accounting of all the ways in which the data were interrogated. This is difficult to do rigorously, especially when analyses evolve iteratively over time. As a result, different studies apply different corrections, leading to a wide range of reported significances. The distinction between frequentist and Bayesian interpretations further complicates matters. In a frequentist framework, significance is typically expressed as a p-value, the probability of obtaining a result at least as extreme as the observed one, assuming the null hypothesis is true. A small p-value suggests that the observed feature is unlikely under the null. In the Bayesian framework, one instead compares the posterior probabilities of competing models. The question is not how unlikely the data are under lambda CDM, but whether an alternative model explains the data better once prior probabilities are taken into account. Bayesian model comparison penalizes additional parameters and complexity, often strongly. These two approaches can lead to very different conclusions. A frequentist analysis may report a low p-value for a particular alignment statistic, suggesting tension with isotropy. A Bayesian analysis may find that no alternative model provides sufficient improvement in likelihood to overcome the prior preference for simplicity. In this view, the anomaly does not justify modifying the standard model. Reported p-values for the axis of evil vary widely across the literature. Some studies have claimed probabilities at the level of 1% or lower for the observed quadrupole-octopole alignment. Others have found much higher probabilities once a posteriori effects and trial factors are accounted for. The spread reflects differences in statistic definition, simulation methodology, foreground treatment, and philosophical approach. Crucially, there is no unique p-value associated with the axis of evil. Each p-value answers a slightly different question. One may ask how often a quadrupole and octopole align within a certain angle. One may ask how often both are planar and aligned. One may ask how often such an alignment also coincides with a physically defined plane. Each question yields a different probability. This multiplicity of questions is not a flaw in the data, but a reflection of the fact that the anomaly itself is not a single well-defined quantity. It is a constellation of related features. Attempting to compress this constellation into a single number inevitably obscures important nuances. Another source of disagreement arises from treatment of foregrounds and masks. Low L modes are sensitive to even small residual contaminations. Different foreground cleaned maps can yield slightly different multipole coefficients, leading to different inferred alignments. While the qualitative features are robust, quantitative significance can shift noticeably. The finite number of Monte Carlo realizations used in simulations also introduces uncertainty. Estimating probabilities at the percent level requires large ensembles to reduce sampling noise. Some early studies relied on relatively small numbers of simulations, leading to unstable tail estimates. Later work has improved this, but differences remain. Underlying all of these issues is a fundamental limitation. Only one sky exists. Statistical inference in cosmology is inherently ensemble-based, but observation provides a single realization. This makes the interpretation of low-probability events especially delicate. A rare event in an ensemble is not forbidden. Someone must observe it. This leads to the central reason why no single significance exists for the axis of evil. Significance is not an intrinsic property of the data alone. It is a property of the data relative to a specified hypothesis, statistic, and inferential framework. Change any of these, and the numerical value changes. In high-precision cosmology, where parameters are constrained by thousands of modes and likelihood surfaces are well-behaved, this ambiguity is minimal. At low multipoles, it becomes unavoidable. The combination of small sample size, geometric complexity, and human pattern recognition makes any claim of significance provisional. As a result, the axis of evil occupies an unusual epistemic status. It is neither a clearly significant anomaly nor a dismissed fluctuation. It persists as a feature that repeatedly appears unusual under simple tests, yet resists decisive statistical condemnation of the standard model. This ambiguity has practical consequences. It motivates continued scrutiny of systematics, development of new statistical tools, and the use of independent datasets such as polarization. At the same time, it encourages caution. Overinterpreting a single number risks mistaking statistical fragility for physical insight. In the end, quantifying the statistical significance of the axis of evil reveals as much about the philosophy of inference as it does about the universe. It exposes the limits of probability in a finite cosmos and highlights the tension between expectation and observation. The absence of a single definitive significance is not a failure of analysis, it is an honest reflection of the problem's structure, where geometry, chance, and interpretation intersect at the largest scales we can observe. Foreground contamination is one of the most persistent and conceptually important issues in interpreting large-scale anomalies in the cosmic microwave background. Any claim about geometry, alignment, or preferred directions at low multipoles must confront the fact that the observed sky is not a pristine image of the early universe. It is a superposition of cosmological signal and multiple layers of astrophysical emission originating much closer to the observer. These foregrounds are not isotropic, not Gaussian, and not random. They possess structure, coherence, and preferred directions by construction. At large angular scales, where the axis of evil manifests, foregrounds are especially problematic. Their spatial variation is smooth, extended, and correlated over large regions of the sky, precisely the regime where low-L modes live. Even small residuals can project strongly onto the quadrupole and octopole. Understanding foreground physics is therefore not a technical detail but a central part of the anomaly's interpretation. One of the dominant galactic foregrounds at microwave frequencies is synchrotron emission. Synchrotron radiation is produced when relativistic electrons spiral around magnetic field lines. In the Milky Way, cosmic ray electrons with energies ranging from hundreds of mega-electron volts to many giga-electron volts propagate through the galactic magnetic field, emitting radiation across a broad range of frequencies. The intensity and spatial distribution of synchrotron emission depend on both the density of relativistic electrons and the structure of the magnetic field. The galactic magnetic field is neither uniform nor isotropic. It has a large-scale ordered component aligned with the galactic disk, as well as turbulent and halo components extending far above and below the plane. As a result, synchrotron emission is strongly anisotropic on the sky, with a pronounced enhancement along the galactic plane and large-scale gradients extending to high latitudes. At low microwave frequencies, synchrotron emission dominates the sky outside the plane as well. Its spectral energy distribution is typically approximated by a power law, with intensity decreasing as frequency increases. However, the spectral index varies across the sky due to changes in electron populations and magnetic field strength. This spatial variation complicates attempts to remove synchrotron contamination using simple scaling relations. Thermal dust emission constitutes another major galactic foreground. Interstellar dust grains, composed of silicates, carbonaceous materials, and other compounds, absorb ultraviolet and optical light from stars and re-emit the energy at infrared and microwave wavelengths. Unlike synchrotron emission, which is non-thermal, Dust emission reflects the physical temperature of the grains, typically tens of Kelvin. Dust emission rises steeply with frequency across the microwave bands relevant to cosmic microwave background observations. It is highly structured, tracing the distribution of gas and star formation in the galaxy. Dust clouds, filaments, and large-scale complexes produce coherent features spanning tens of degrees on the sky. Even at high galactic latitudes, diffuse dust emission persists and exhibits large-scale asymmetries. Crucially, dust emission is polarized and aligned with the galactic magnetic field. This alignment introduces directional structure that can project onto low-L modes. While polarization is a separate observable, temperature maps are also affected through total intensity emission. Removing dust contamination requires accurate modeling of both its spatial distribution and spectral behavior. Free radiation, also known as Bremsstrahlung, arises from interactions between free electrons and ions in ionized gas. When electrons are deflected by the electric fields of ions, they emit radiation across a broad spectrum. In the Milky Way, free emission is associated with ionized regions such as H2 regions, diffuse ionized gas, and the warm ionized medium. Free emission has a relatively flat spectral dependence in the microwave regime compared to synchrotron and dust. It does not dominate at high latitudes, but it contributes non-negligibly at large angular scales. Its spatial distribution follows regions of ionized gas, which are themselves structured and correlated with other galactic components. Although free emission is generally less problematic than synchrotron or dust at the frequencies used by WMAP and Planck, its contribution is not negligible when precision at the level of microkelvin matters. Residual free contamination can subtly bias low-L modes, especially if its spatial template overlaps with the geometry of the quadrupole or octopole. Beyond galactic emission, zodiacal light introduces an additional, more local foreground. Zodiacal emission arises from interplanetary dust particles distributed throughout the inner solar system. These particles absorb sunlight and re-emit it primarily at infrared wavelengths, but a faint contribution extends into the microwave regime. Zodiacal light is strongly tied to the ecliptic plane because the dust cloud is concentrated in the plane of planetary orbits. Its spatial distribution is therefore highly anisotropic and explicitly aligned with a physically defined plane associated with the observer's environment. This fact alone makes zodiacal emission particularly concerning in discussions of alignments near the ecliptic. At microwave frequencies, zodiacal emission is much weaker than galactic foregrounds. However, its large-scale, smooth structure means that even a small residual could project onto low multipoles. Accurately modelling zodiacal emission requires detailed knowledge of the dust distribution in the solar system and its emissivity, which is constrained primarily by infrared observations. Because each foreground component has a distinct spectral signature, frequency dependence tests play a central role in distinguishing cosmological signal from contamination. The cosmic microwave background has a precisely known blackbody spectrum. Foregrounds deviate from this spectrum in characteristic ways. By observing the sky at multiple frequencies, one can exploit these differences to separate components. In practice, this separation is imperfect. Spectral indices vary spatially. Components overlap in frequency space. Instrumental noise and calibration uncertainties further complicate the picture. At low multipoles, where signal-to-noise is already limited by cosmic variance, these complications are magnified. Component separation techniques are designed to address this challenge. These methods combine multi-frequency data to extract a map intended to represent the cosmological signal while suppressing foregrounds. Different techniques make different assumptions. Some rely on external templates for known foregrounds. Others use statistical independence or minimal variance criteria to separate components blindly. Examples include internal linear combination methods, maximum entropy approaches, and parametric fitting techniques. Each has strengths and weaknesses. Blind methods reduce reliance on foreground models, but may leave residual contamination if assumptions are violated. Parametric methods can be more precise, but depend on the accuracy of the models. Crucially, component separation is not a single operation, but a pipeline. Choices about weighting, masking, smoothing, and calibration propagate into the final maps. At high multipoles, differences between methods are often negligible. At low multipoles, they can materially affect the inferred geometry of the sky. Masking and sky cuts provide another line of defense against foreground contamination. By excluding regions of the sky where foreground emission is strongest, typically near the galactic plane, one reduces the risk of residual contamination. However, masking introduces its own complications. Removing large portions of the sky breaks rotational invariance and mixes multipoles. When part of the sky is masked, the spherical harmonic coefficients are no longer independent. Power from one multipole leaks into others. This leakage is particularly severe at low L, where the number of modes is small. Correcting for these effects requires careful treatment and introduces additional uncertainty. There is a trade-off between contamination and completeness. Aggressive masking reduces foregrounds but increases mode coupling and statistical noise. Conservative masking preserves sky coverage but risks leaving residual emission. Different analyses adopt different compromises, leading to variations in low-L results. Residual contamination risks remain even after the most careful cleaning. Foregrounds are not perfectly modelled. Small mismatches between assumed and actual spectral behaviour can leave imprints that mimic or distort cosmological features. Because the axis of evil involves alignment with physically meaningful planes, any residual tied to the galaxy or the solar system is particularly suspect. This is why foregrounds cannot be dismissed simply because the anomaly persists across different maps. Consistency across maps is necessary but not sufficient to establish cosmological origin. Many cleaning methods share underlying assumptions or data inputs. A common residual can survive multiple pipelines. At the same time, the foreground explanation faces its own challenges. The quadrupole-octopole alignment does not align cleanly with the galactic plane, where contamination is strongest, nor does it coincide perfectly with any single known foreground template. This ambiguity complicates simple attribution to contamination. The debate over foregrounds thus remains unresolved. Foregrounds provide a plausible mechanism for introducing large-scale anisotropy and preferred directions. Yet no specific foreground component has been definitively shown to reproduce the observed geometric features without also producing additional discrepancies. What foreground analysis has established beyond doubt is the fragility of low-L inference. At these scales, cosmology operates at the boundary between signal and systematic. The difference between a profound challenge to isotropy and a mundane artifact can hinge on micro-Kelvin level residuals spread over tens of degrees. As a result, any interpretation of the axis of evil must be conditional. It must acknowledge that foreground contamination is not an external nuisance to be subtracted away, but an intrinsic part of the measurement problem. Until foreground physics, component separation, and large-scale systematics are fully mastered, geometric anomalies at the largest angular scales will remain suspended between cosmology and astrophysics. Instrumental and data processing systematics occupy a distinct conceptual category from astrophysical foregrounds, yet their potential impact on large-scale cosmic microwave background anomalies is equally serious. Unlike foregrounds, which originate from known physical sources, systematics arise from the interaction between the sky signal, the instrument, and the analysis pipeline. They are not external contaminants added to the data, but distortions introduced during measurement and reconstruction. At low multipoles, where the signal is smooth, extended, and weakly constrained by statistics, such distortions can project coherently and produce patterns that resemble genuine cosmological features. One of the most important instrumental effects is beam asymmetry. No real telescope observes the sky with a perfectly circular, isotropic beam. The instrumental beam describes how radiation from a point source is spread over neighbouring pixels. In practice, beams are slightly elliptical, frequency-dependent, and vary across the focal plane. These asymmetries are usually small, but their effect accumulates over repeated observations and can imprint subtle directional signatures on the reconstructed maps. At small angular scales, beam asymmetries primarily distort point sources or high L power. At large angular scales, their influence is indirect. As the instrument scans the sky, beam asymmetries interact with the scanning pattern. If certain directions are observed preferentially with a particular beam orientation, the convolution of sky signal and beam can introduce anisotropic smoothing. Over the full mission lifetime, this can lead to large-scale patterns aligned with the scanning geometry. Scanning strategy itself is therefore a critical factor. Both WMAP and Planck employed highly structured scanning patterns designed to provide uniform sky coverage and stable calibration. These strategies involved spinning the spacecraft and precessing the spin axis in a controlled way, producing characteristic paths across the sky. While these patterns were optimized to minimize systematics, they inevitably introduced preferred directions in the time-ordered data. In principle, an ideal scan would cover all orientations equally for every point on the sky. In practice, coverage is never perfectly uniform. Some regions are observed more frequently or with a narrower range of scan angles. This uneven coverage can couple to beam asymmetries and produce residual anisotropy in the final maps. Importantly, the resulting patterns are smooth and coherent, making them difficult to distinguish from genuine low L modes. Noise anisotropy adds another layer of complexity. Instrumental noise is not uniformly distributed across the sky. Regions near the ecliptic poles, for example, are often observed more frequently than regions near the ecliptic plane due to scanning geometry. This leads to spatial variations in noise amplitude. While noise is usually treated as uncorrelated and random, anisotropic noise can bias large-scale statistics if not properly accounted for. At high multipoles, noise anisotropy is largely irrelevant because the signal dominates and averaging suppresses noise contributions. At low multipoles, however, the small number of modes means that noise structure can leak into the estimated spherical harmonic coefficients. This leakage is especially problematic if noise correlates with scanning directions or beam orientation. Dipole subtraction introduces yet another potential source of systematic error. The largest signal in the cosmic microwave background sky is not the primordial anisotropy, but the dipole induced by the motion of the observer relative to the CMB rest frame. This dipole is orders of magnitude larger than all other anisotropies combined. Removing it accurately is therefore essential. Dipole subtraction is conceptually straightforward. One estimates the dipole amplitude and direction, then subtracts it from the time-ordered data or maps. In practice, small uncertainties in calibration, pointing, or gain can lead to imperfect subtraction. Residual dipole contamination can project onto low multipoles, particularly the quadrupole and octopole, because these modes represent the next slowest variations across the sky. Moreover, the dipole direction is closely tied to the solar system's motion, which defines a physically meaningful axis. Any residual correlated with this axis can mimic a preferred direction in the low L modes. Even tiny fractional errors in dipole removal can produce microkelvin level effects that matter at the largest angular scales. Map-making algorithms sit at the heart of the pipeline connecting raw measurements to final sky maps. These algorithms combine time-ordered data, pointing information, calibration parameters, and noise models to reconstruct the temperature field on the sky. Different map-making approaches make different assumptions about noise correlations, baseline offsets, and systematic drifts. At low multipoles, map-making choices are particularly influential. Baseline subtraction methods, which remove slow drifts in the instrument response, can inadvertently remove or distort genuine large-scale sky signal. Conversely, insufficient baseline removal can leave striping patterns aligned with scan paths. These stripes are typically low-level, but their coherence across large angles makes them relevant for ELL equals 2 and L equals 3. The challenge is that map-making systematics do not manifest as obvious artifacts. They do not appear as sharp features or localized defects. Instead, they subtly alter the global structure of the map. Distinguishing such effects from cosmological signal requires careful end-to-end simulations that propagate known instrumental properties through the full pipeline. Cross-channel consistency tests are therefore essential. Both WMAP and Planck observed the sky in multiple frequency channels using different detectors and optics. A genuine cosmological signal should appear consistently across channels once foregrounds are removed. Instrument-specific systematics, by contrast, may vary between channels. Analyses of low-L anomalies have therefore compared quadrupole and octopole patterns derived independently from different frequency maps. Broad consistency has generally been found, which argues against simple single-channel systematics. However, this consistency does not rule out systematics that are common across channels, such as those arising from shared scanning strategies or calibration procedures. Differences between independent pipelines provide another important diagnostic. For both WMAP and Planck, multiple teams developed independent data processing pipelines using different map-making algorithms, calibration schemes, and foreground treatments. Comparing results across pipelines helps identify robust features and isolate pipeline-dependent artifacts. In practice, low-L features show some sensitivity to pipeline choices. The detailed shapes and orientations of the quadrupole and octopole can shift slightly depending on how maps are constructed and cleaned. While the existence of an alignment is relatively robust, its precise statistical significance varies. This sensitivity underscores the role of subtle systematics that are difficult to eliminate completely. The key reason systematics can mimic alignments lies in the nature of the signal being studied. Low multipoles represent smooth global patterns. Any process that introduces coherent structure over large angular scales can project onto these modes. Scanning strategies, beam asymmetries, and baseline errors all naturally produce large-scale coherence. Furthermore, many systematics are tied to physically meaningful directions. The spin axis of the spacecraft, the ecliptic plane, the dipole direction, or the galactic plane. Alignments involving these directions are therefore especially suspect. When an anomaly appears correlated with such axes, the burden of proof shifts toward demonstrating that it cannot arise from known instrumental effects. At the same time, systematics explanations face their own constraints. The alignment observed in the cosmic microwave background does not align perfectly with any single obvious instrumental axis. It is close to the ecliptic, but not exactly coincident. It is not trivially reproduced by known scanning patterns. This ambiguity weakens simple systematic explanations. The reality is that instrumental and pipeline systematics occupy a grey zone. They are neither easily dismissed nor easily confirmed as the sole cause of the axis of evil. Their effects are subtle, distributed, and entangled with foreground removal and statistical inference. They demand a level of scrutiny that goes beyond standard validation procedures. What this analysis makes clear is that low-L cosmology operates at the limits of experimental control. At these scales, microkelvin level uncertainties accumulated over years of observation and processing can matter. The distinction between cosmological signal and systematic artifact becomes less clear-cut than at smaller scales. This does not imply that the observed alignments are artifacts. It implies that confidence must be conditional. Any claim about preferred directions or geometric anomalies must be framed in the context of known instrumental behaviors and the limits of current pipelines. Systematics mimic alignments not because of malicious coincidence, but because geometry is hard. Measuring smooth patterns on a sphere with a moving, imperfect instrument is intrinsically challenging. The fact that the axis of evil remains a topic of debate reflects not a failure of experimental cosmology, but its remarkable sensitivity. At the largest scales, where the universe speaks most directly about its origins, the margin between signal and artifact becomes vanishingly thin. The arrival of Planck data marked the most comprehensive observational reassessment of large-scale anomalies in the cosmic microwave background to date. Planck was conceived explicitly to improve upon WMAP in nearly every instrumental dimension: angular resolution, sensitivity, frequency coverage, calibration accuracy, and control of systematics. As a result, expectations were high that Planck would either decisively confirm the axis of evil as a genuine cosmological feature or dissolve it as an artifact of limited data and analysis choices. Planck's angular resolution exceeded that of WMAP by a significant margin, reaching arc-minute scales in its highest frequency channels. Its sensitivity to temperature fluctuations was correspondingly improved, with lower noise per pixel and more uniform sky coverage. Importantly for large-scale analysis, Planck also observed the sky across a broader range of frequencies, extending well into the sub-millimeter regime where thermal dust emission dominates. This allowed foreground modelling and component separation to be performed with unprecedented sophistication. From the standpoint of low multipoles, however, higher resolution was not the primary advantage. The quadrupole and octopole are already fully resolved by WMAP. Instead, Planck's contribution lay in improved signal-to-noise, better foreground discrimination, and independent instrumental systematics. If the alignment observed by WMAP were an artifact of noise, beam effects, or foreground residuals, Planck offered a stringent test. Planck's temperature maps confirmed many of WMAP's large-scale findings. The low quadrupole amplitude persisted. The suppression of large-scale power remained evident. More importantly, for the axis of evil, the quadrupole-octopole alignment did not disappear. When low-L modes were reconstructed from Planck temperature data, their orientations remained broadly consistent with those inferred from WMAP. This persistence was significant. Planck employed different detectors, optics, scanning strategies, and calibration pipelines. The fact that the low-L geometry survived these changes strongly suggested that the anomaly was not a simple instrumental artifact tied uniquely to WMAP. At the same time, Planck analyses revealed subtle differences in the detailed morphology of the quadrupole and octopole, underscoring the sensitivity of low-L features to map-making choices. A crucial new element introduced by Planck was high-quality polarization data. Polarization provides an independent probe of the same primordial perturbations that generate temperature anisotropies. Because polarization arises from Thomson scattering in the presence of local quadrupole anisotropies at recombination, it encodes information about large-scale structure in a different way. If the axis of evil reflects genuine early universe physics, some imprint might be expected in polarization as well. In practice, polarization data at the lowest multipoles are far noisier than temperature data. Large-scale polarization is difficult to measure due to instrumental systematics, foreground polarization from dust and synchrotron emission, and limited signal amplitude. Nevertheless, Planck provided the first opportunity to test whether low-L temperature anomalies were accompanied by corresponding polarization features. analyses of Planck polarization data did not reveal a clear analogue of the quadrupole-octopole alignment. The polarization maps were broadly consistent with statistical isotropy within large uncertainties. This absence of a strong polarization counterpart was interpreted in different ways. Some argued that it weakened the case for a cosmological origin of the axis of evil, since primordial physics should affect both temperature and polarization. Others noted that polarization constraints were simply too weak at low L to draw firm conclusions. Importantly, the absence of evidence in polarization was not evidence of absence. The expected polarization signal associated with large-scale temperature modes is intrinsically small, and cosmic variance further limits interpretability. As a result, polarization neither confirmed nor decisively refuted the anomaly. Planck data also prompted a reassessment of statistical significance. With improved foreground cleaning and better characterization of systematics, some alignment measures appeared slightly less anomalous than in early WMAP-based studies. In particular, when conservative masks and strict a posteriori corrections were applied, p-values increased. In some analyses, the quadrupole-octopole alignment was found to lie comfortably within the range of rare but acceptable realizations under lambda CDM. Other analyses, using different statistics or less aggressive corrections, continued to find low probabilities. The range of reported significances narrowed somewhat compared to the WMAP era, but disagreement remained. What changed most was not the existence of the anomaly, but confidence in its interpretation. Internal consistency checks became a central feature of Planck's reassessment. Low-L modes were reconstructed independently from different frequency subsets, different component separation methods, and different map-making pipelines. While details varied, the gross geometry of the quadrupole and octopole was stable across these tests. This stability argued against foreground or instrumental explanations that depended sensitively on frequency or detector. At the same time, Planck teams emphasized the sensitivity of low-L results to methodological choices. Small differences in masking, inpainting, or likelihood construction could shift alignment measures noticeably. This sensitivity reinforced the view that low-L cosmology exists in a regime where inference is intrinsically delicate. As Planck analyses matured, a tension emerged not in the data, but in interpretation. Conservative interpretations emphasized cosmic variance, a posteriori bias, and the lack of a compelling theoretical model that naturally produces the observed alignment without fine-tuning. From this perspective, the axis of evil was regarded as an interesting statistical curiosity, but not evidence for new physics. More aggressive interpretations stressed persistence across datasets, robustness across pipelines, and the coherence of multiple geometric anomalies. They argued that the probability of all these features arising simultaneously by chance was small enough to warrant serious consideration of isotropy violation, unconventional inflationary dynamics, or non-trivial cosmic topology. Planck's official publications tended toward caution. While acknowledging the existence of large-scale anomalies, including alignments and power suppression, they stopped short of claiming any breakdown of lambda CDM. The anomalies were catalogued, quantified, and discussed, but not elevated to the status of confirmed discrepancies requiring theoretical revision. This cautious stance reflects an important methodological principle. Planck was designed to test the standard model with maximal rigor, not to overinterpret marginal deviations. In the absence of decisive polarization confirmation or a compelling alternative model, restraint was justified. At the same time, Planck did not close the case. By confirming the persistence of low-L anomalies in an independent experiment, it ensured that the axis of evil could not be dismissed as an artifact of a single dataset. It reframed the question from, does the anomaly exist, to, what does its existence mean, if anything? In this sense, Planck's contribution was transformative. It did not provide a final answer, but it elevated the discussion to a higher level of precision and skepticism. The anomaly survived contact with the most sophisticated cosmic microwave background experiment ever built, but it emerged more ambiguous, not less. The tension between conservative and aggressive interpretations remains unresolved because it reflects a deeper tension in cosmology itself. The largest scales probe the earliest conditions of the universe, but they are also where statistical power is weakest. Planck sharpened our view of this boundary. It showed that even with extraordinary data quality, some questions remain inherently probabilistic. What Planck ultimately demonstrated is that the axis of evil is not a simple artifact to be removed, nor a clear signal demanding new physics. It is a persistent geometric peculiarity that sits at the edge of what cosmology can currently decide. Whether future data will clarify its origin, or whether it will remain an enduring reminder of the limits of inference, is a question that Planck, despite its power, could not fully resolve. The axis of evil does not exist in isolation. It is part of a broader collection of large-scale anomalies that challenge the assumption of perfect statistical isotropy in the cosmic microwave background. Each of these anomalies, taken individually, is subtle and statistically fragile. Taken together, they form a pattern that has motivated sustained scrutiny of the largest angular scales. Understanding the axis of evil therefore requires placing it within this wider context. One of the earliest and most widely discussed isotropy anomalies is hemispherical power asymmetry. This effect refers to the observation that the amplitude of temperature fluctuations differs systematically between two opposite hemispheres of the sky. When the sky is divided along a particular axis, one hemisphere appears to have higher variance than the other across a range of angular scales. This asymmetry was first identified in WMAP data and later confirmed with some variation in Planck observations. The effect is most pronounced at large angular scales and appears to extend to intermediate multipoles as well. Importantly, the hemispheres that maximize the asymmetry are not aligned with standard coordinate systems such as the galactic plane, but instead define their own preferred axis. Quantitatively, the hemispherical asymmetry is often characterized by comparing the power spectrum computed separately on two hemispheres. Under statistical isotropy, differences in power should be consistent with cosmic variance. The observed asymmetry exceeds these expectations in certain multipole ranges, though the exact significance depends on how the hemispheres are chosen and how a posteriori corrections are applied. To model this effect, researchers have introduced dipolar modulation models. In these models, the temperature field is described as an isotropic Gaussian field multiplied by a slowly varying dipolar modulation. Physically, this corresponds to a large-scale gradient in fluctuation amplitude across the sky. Mathematically, it introduces coupling between multipoles that would otherwise be independent. Dipolar modulation provides a compact phenomenological description of hemispherical asymmetry. It captures the idea that one side of the sky is slightly hotter or more structured than the other in a statistical sense. When fitted to the data, such models can reproduce the observed asymmetry and yield an estimate of the modulation amplitude and direction. Crucially, the preferred direction inferred from dipolar modulation analyses is often found to be close to the axis, associated with the quadrupole-octopole alignment. This proximity has fueled speculation that these anomalies may share a common origin. However, proximity alone does not establish causality. Different statistical measures applied to the same data can yield correlated axes even if the underlying effects are unrelated. Parity asymmetry represents another class of large-scale anomaly. Parity, in this context, refers to the behavior of temperature fluctuations under spatial inversion. One can decompose the temperature field into contributions from even and odd multipoles. Under statistical isotropy and Gaussianity, there is no reason for one parity to dominate over the other. Observationally, the cosmic microwave background appears to exhibit an imbalance between even and odd multipoles at low L. In particular, odd multipoles seem to carry more power than even ones over a certain range. This imbalance manifests as a lack of correlation between antipodal points on the sky and alters the large-angle correlation function. Parity asymmetry is closely related to the low quadrupole amplitude. The quadrupole, being the lowest even multipole, plays a disproportionate role in shaping parity statistics. Its suppression contributes significantly to the observed imbalance. As a result, parity asymmetry cannot be treated as entirely independent of the quadrupole anomaly. The low quadrupole amplitude itself predates the axis of evil discussion and remains one of the simplest large-scale anomalies. As noted in earlier datasets, the measured quadrupole power is lower than the ensemble mean predicted by lambda CDM. While this is not statistically extreme given cosmic variance, it becomes more intriguing when considered alongside other anomalies that involve the same multipole. When quadrupole suppression, quadrupole-octopole alignment, hemispherical asymmetry, and parity imbalance are viewed together, an obvious question arises. Are these manifestations of a single underlying deviation from isotropy, or are they unrelated statistical flukes that happen to coexist in one realization? Addressing this question requires a formalism capable of capturing departures from statistical isotropy in a unified way. One such framework is the bipolar spherical harmonics formalism. This approach generalizes the usual spherical harmonic expansion by allowing correlations between different multipoles. Instead of assuming diagonal covariance in harmonic space, it parametrizes anisotropy through off-diagonal terms. In the bipolar spherical harmonics representation, any statistically anisotropic signal can be decomposed into modes that explicitly encode preferred directions and scales. This allows one to test for specific patterns of anisotropy, such as dipolar modulation or quadrupolar distortion, in a systematic and rotationally covariant way. Applying this formalism to cosmic microwave background data reveals that several isotropy anomalies can be described using a small number of anisotropic modes. In particular, dipolar modulation naturally induces correlations between multipoles differing by 1 unit in L. This provides a mathematical link between hemispherical asymmetry and alignments involving low multipoles. However, not all anomalies fit neatly into a single template. Parity asymmetry, for example, does not correspond straightforwardly to a simple directional modulation. Its origin may lie in initial conditions, cosmic variance, or the specific realization of phases rather than a coherent anisotropic mechanism. Similarly, the axis of evil involves correlations between specific multipoles rather than a smooth modulation across scales. While dipolar modulation can influence low L geometry, it does not automatically produce strong quadrupole-octopole alignment without additional assumptions or tuning. Statistical studies attempting to assess whether anomalies are independent or linked have reached mixed conclusions. Some analyses find that conditioning on one anomaly reduces the significance of others, suggesting partial dependence. Others find that multiple anomalies persist even after accounting for correlations, implying that chance alignment of rare features cannot be ruled out. A central difficulty is that all these anomalies draw on the same limited pool of information, the lowest multipoles of a single sky. With so few degrees of freedom, statistical independence is hard to establish. Apparent correlations may arise simply because multiple tests are probing the same underlying modes. Moreover, a posteriori selection plays a major role. Anomalies are identified because they appear unusual in the observed data. Their coexistence may therefore reflect the way the data are interrogated rather than a physical connection. Untangling these effects requires careful simulation-based studies that account for the full space of possible tests. Despite these challenges, the broader isotropy anomalies share an important qualitative feature. They all reside at large angular scales. They all involve departures from the simplest expectations of isotropy and randomness. and they all weaken or disappear at smaller scales where statistical power is greater and physical modelling is more robust. This clustering in scale suggests that if a physical explanation exists, it likely operates at or before the epoch when the largest modes were established. Alternatively, it suggests that cosmic variance and observational limitations dominate inference at these scales, creating fertile ground for apparent anomalies. At present, no consensus exists on whether the axis of evil and related isotropy anomalies are manifestations of a single underlying phenomenon or independent statistical accidents. What is clear is that they cannot be fully understood in isolation. Each anomaly informs the interpretation of the others, either by reinforcing a pattern or by diluting significance through shared degrees of freedom. The broader picture that emerges is one of tension rather than contradiction. The lambda CDM model continues to describe the vast majority of observations with remarkable accuracy. Yet at the largest scales, where the universe offers the fewest data points and the deepest insights into initial conditions, its assumptions are tested most severely. Whether these tests ultimately reveal new physics or reaffirm the power of statistical reasoning remains an open question. What the broader isotropy anomalies demonstrate beyond doubt is that the geometry of the cosmic microwave background at the largest scales remains one of the most conceptually challenging frontiers in modern cosmology. Attempts to explain the axis of evil through exotic cosmological physics begin by relaxing one of the deepest assumptions of the standard model, exact rotational invariance of the primordial universe. Within lambda CDM, statistical isotropy is not an accident, but a consequence of the simplest inflationary dynamics. To generate a preferred direction, one must modify that dynamics in a controlled way, introducing new fields, couplings, or background structures that survive inflation without being exponentially erased. The most general class of proposals falls under the heading of anisotropic inflation. In these scenarios, the expansion rate during inflation is not exactly the same in all spatial directions. Instead of a perfectly isotropic de Sitter-like phase, space-time possesses a small but persistent anisotropy, often associated with a background field that defines a direction. In conventional inflation driven by a scalar field, any initial anisotropy in the expansion decays extremely rapidly. This behavior is formalized in the cosmic no-hair theorem, which states that de Sitter expansion erases classical anisotropies. To evade this outcome, anisotropic inflation models introduce additional ingredients that continuously source anisotropy, preventing it from decaying. One widely studied approach involves coupling the inflaton to a vector field. Vector fields naturally carry directional information. If a vector field acquires a non-zero vacuum expectation value during inflation, it can define a preferred spatial direction and imprint that direction onto primordial perturbations. Vector field inflation models take many forms. In some, the vector field is subdominant in energy density, but coupled to the inflaton in such a way that its fluctuations are amplified. In others, the vector field contributes directly to the stress-energy tensor driving inflation. In either case, maintaining a stable background vector configuration without introducing ghosts or instabilities is technically challenging. When successful, these models predict specific signatures. The power spectrum of primordial perturbations becomes direction-dependent. Instead of depending only on the magnitude of the wave vector, it acquires dependence on its orientation relative to the preferred direction. This leads to statistical anisotropy in the cosmic microwave background, often parameterized as a quadrupolar modulation of power. Such anisotropy can, in principle, generate correlations between low multipoles and produce alignments similar to those observed. However, the predicted anisotropy is typically smooth and scale-independent, affecting a wide range of multipoles. The axis of evil, by contrast, is most pronounced at the very lowest L values and weakens rapidly at smaller scales. Matching this scale dependence is difficult. Primordial magnetic fields provide another possible source of anisotropy. Magnetic fields are inherently vectorial and can survive cosmic expansion if generated early enough. If a coherent magnetic field existed during or before inflation, it could introduce a preferred direction and influence the evolution of perturbations. Models of magnetogenesis during inflation attempt to generate such fields by breaking the conformal invariance of electromagnetism. This typically requires coupling the electromagnetic field to the inflaton or to curvature. While this can amplify magnetic fluctuations, it often leads to severe back reaction problems. The energy density in the generated fields can grow large enough to disrupt inflation itself. Even when viable, primordial magnetic fields tend to produce a broad range of observational effects. They induce non-Gaussianity, modify polarization patterns, and affect the matter-power spectrum. Current observational constraints strongly limit their amplitude. Producing a field strong enough to affect the quadrupole and octopole while remaining consistent with these constraints requires delicate tuning. Preferred frame models take a more radical approach. Instead of introducing a specific field configuration, they posit that space-time itself possesses a built-in preferred frame or direction at a fundamental level. This can arise in theories with spontaneous breaking of Lorentz symmetry or in extensions of gravity that include vector or tensor backgrounds. In such models, rotational invariance is not exact even at the most fundamental level. Cosmological perturbations inherit this asymmetry, leading to direction-dependent correlations. While mathematically consistent frameworks exist, they face stringent constraints from laboratory experiments, astrophysical observations, and the success of relativistic invariance across a vast range of scales. Breaking rotational invariance in the early universe also has consequences beyond the cosmic microwave background. It affects the propagation of gravitational waves, alters the statistics of large-scale structure, and can leave imprints in polarization and lensing signals. Any viable model must thread a narrow path between producing a detectable large-scale anomaly and avoiding conflicts with these other observables. A recurring difficulty across exotic explanations is the mismatch between predicted and observed signatures. Most models that introduce anisotropy do so in a way that affects many scales uniformly. The axis of evil, however, is a low L phenomenon. Its apparent confinement to the largest angular scales suggests either a mechanism that operates only at the longest wavelengths or a coincidence amplified by cosmic variance. Another challenge is the absence of strong non-Gaussian signals. Many anisotropic models predict measurable departures from Gaussianity in the temperature field. Observations constrain such departures tightly. The lack of clear non-Gaussian features associated with the axis of evil limits the range of acceptable models. Fine-tuning emerges as a central issue. To produce an effect that is large enough to be noticed but small enough to evade existing constraints, parameters must often be adjusted with great precision. The strength of anisotropy, the duration of inflation, the coupling constants, and the initial conditions all need to be set within narrow ranges. From a theoretical perspective, this fine-tuning undermines the appeal of exotic explanations. Inflation was originally motivated in part by its ability to explain observed isotropy without special initial conditions. Introducing mechanisms that require carefully balanced parameters risks replacing one unexplained feature with another. Moreover, exotic models often struggle to explain why the preferred direction aligns, even approximately, with observer-related planes such as the ecliptic. Cosmological mechanisms should produce directions uncorrelated with local structures. Any apparent alignment with solar system geometry therefore weakens the case for a primordial origin unless a compelling explanation is provided. This does not mean that exotic cosmological explanations are ruled out. It means that none currently offers a simple, robust account of the axis of evil that improves decisively on lambda CDM. Each can reproduce some aspects of the data under specific conditions, but none naturally reproduces the full set of observed features without additional assumptions. As a result, exotic explanations remain speculative. They serve an important role as consistency checks on the foundations of cosmology, demonstrating how deeply isotropy is woven into our standard theories. At the same time, their difficulties highlight how demanding the observational constraints are. The axis of evil thus occupies an uncomfortable position for theory. It is intriguing enough to motivate departures from standard assumptions, yet subtle enough to resist clean explanation. For now, exotic cosmological models illuminate the kinds of physics that could, in principle, generate preferred directions, but they also reveal how hard it is to do so without paying a high price in complexity, fine-tuning, or conflict with other observations. Late-time and local explanations approach the axis of evil from a fundamentally different angle than exotic early universe physics. Instead of modifying inflation or primordial initial conditions, these explanations ask whether processes occurring long after recombination or features tied to the observer's location could imprint large-scale anisotropy onto the cosmic microwave background. This perspective shifts attention from the surface of last scattering to the evolving universe between then and now. The most widely discussed late-time contribution to large-scale temperature anisotropy is the integrated Sachs-Wolf effect. This effect arises when cosmic microwave background photons traverse time-evolving gravitational potentials on their journey to the observer. In a universe dominated purely by matter, large-scale gravitational potentials remain constant in time, and photons entering and exiting such potentials gain and lose equal amounts of energy. No net temperature shift occurs. In a universe with dark energy or spatial curvature, this balance is broken. As the universe accelerates, gravitational potentials associated with large-scale structure decay with time. Photons climbing out of a potential well that is shallower than when they entered emerge with a net energy gain. This produces temperature anisotropies correlated with the distribution of matter at late times. The integrated Sachs-Wolf effect operates primarily at large angular scales. Its contribution is strongest for modes corresponding to wavelengths comparable to the horizon size at late times. This makes it, in principle, relevant to the quadrupole and octopole. Because it is sourced by structure at relatively low redshift, it depends on the actual distribution of matter in the nearby universe. This dependence makes the effect inherently anisotropic in any single realization. The large-scale structure surrounding the observer is not isotropic. Superclusters, voids, and filaments define a complex and asymmetric mass distribution. As a result, the integrated Sachs-Wolf effect can introduce direction-dependent temperature fluctuations on the largest scales. However, the magnitude of this effect is limited. In lambda CDM, the integrated Sachs-Wolf contribution to the quadrupole and octopole is expected to be small compared to the primordial signal. While it can modify the large-scale pattern, it cannot dominate it. Simulations show that it can enhance or suppress existing modes, but producing a strong alignment requires a highly specific configuration of large-scale structure. Closely related is the Rees-Siama effect, which arises from nonlinear evolution of gravitational potentials. As structures collapse and virialize, their gravitational fields evolve in a nonlinear fashion. Photons passing through such regions experience small net energy shifts. Unlike the integrated Sachs-Wolf effect, which is linear and operates on very large scales, the Rees-Siama effect is strongest in dense, rapidly evolving regions such as clusters. Because the Rees-Siama effect is localized and nonlinear, its contribution is generally confined to small angular scales. Its impact on the quadrupole and octopole is negligible in standard cosmology. While it is sometimes invoked in discussions of late-time effects, detailed calculations show that it cannot account for large-scale alignments or coherent planar features. Another line of reasoning considers whether the large-scale structure of the universe itself might be aligned in such a way as to imprint correlated anisotropy on the cosmic microwave background. If the distribution of nearby matter possessed a preferred axis, this could influence the integrated Sachs-Wolf signal and potentially bias low multipoles. The local universe is indeed anisotropic. Galaxy surveys reveal prominent structures such as superclusters, filaments, and voids extending over hundreds of megaparsecs. These structures are not randomly oriented with respect to the observer. Their geometry reflects the specific realization of structure formation in our cosmic neighborhood. The local supercluster, sometimes referred to as the Laniakea region, defines a large-scale flow pattern and mass concentration that influences galaxy motions over tens of megaparsecs. Its flattened geometry and associated filamentary structures introduce anisotropy into the nearby matter distribution. It is natural to ask whether this anisotropy could correlate with the observed CMB anomalies. Studies attempting to link the axis of evil to local supercluster geometry have produced mixed results. While some alignments between low L-axes and directions associated with local structure have been reported, these correlations are generally weak and sensitive to how structures are defined. Moreover, the redshift range over which the integrated Sachs-Wolf effect is significant extends well beyond the local supercluster, diluting the influence of any single structure. Bulk flow correlations provide another potential connection. Observations indicate that galaxies exhibit coherent peculiar velocities over large volumes, sometimes described as bulk flows. These flows reflect large-scale gravitational gradients and may be associated with anisotropic matter distributions. If such flows were unusually strong or extended, they could, in principle, correlate with large-scale CMB features. However, the connection between bulk flows and temperature anisotropies is indirect. Peculiar velocities primarily affect the CMB through Doppler effects and kinetic Sunyaev-Zeldovich contributions, which are small at large scales. While bulk flows trace anisotropic structure, their ability to generate coherent quadrupole-octopole alignment is limited. Observer location bias introduces a more subtle consideration. Cosmological predictions often assume that the observer is located at a statistically typical position in the universe. In reality, the observer resides in a specific environment, inside a galaxy, within a group, embedded in a supercluster, moving with a particular velocity relative to the cosmic rest frame. This specificity can matter at the largest scales. The observed CMB sky is not an ensemble average, but a conditional realization given the observer's location and motion. Certain alignments or asymmetries may be more likely for observers situated in particular environments. From this perspective, the axis of evil could reflect a selection effect rather than a fundamental violation of isotropy. Quantifying observer location bias is difficult. It requires modeling not just the universe, but the conditional probability of observing certain CMB features given the existence of observers in specific regions. While anthropic reasoning is often invoked in discussions of cosmological constants, its application to CMB geometry is far less developed. Despite their conceptual appeal, late-time and local explanations face significant limits. The most important is amplitude. The observed low-L anomalies are comparable in magnitude to the primordial signal itself. Late-time effects, by contrast, are typically subdominant corrections. Producing strong geometric correlations would require unusually favorable circumstances. Another limitation is coherence. The axis of evil involves correlated geometry across multiple multipoles. Late-time effects tend to add incoherent contributions superimposed on the primordial pattern. While they can distort or modulate existing modes, generating a shared preferred axis for both the quadrupole and octopole is difficult without fine-tuning. There is also the issue of scale dependence. Late-time effects are not sharply confined to the lowest multipoles. They affect a range of scales depending on the size and evolution of structures. The apparent concentration of anomalies at ELL equals 2 and L equals 3 is not a natural outcome of these mechanisms. Finally, many late-time explanations implicitly rely on correlations with the observer's motion or environment. This raises the expectation that alignments should track well-defined local directions, such as the dipole direction or the galactic plane. The observed axis does not align cleanly with any single such direction, complicating interpretation. Taken together, late-time and local explanations offer plausible contributions to large-scale anisotropy, but they struggle to account for the full phenomenology of the axis of evil. They likely play a role in shaping the observed sky at some level, particularly through the integrated Sachs-Wolf effect. Yet their capacity to generate strong, coherent, and scale-specific alignments appears limited. This does not render them irrelevant. On the contrary, they emphasize the importance of viewing the cosmic microwave background as a composite signal shaped by physics across cosmic time. They remind us that the observed sky is not a pristine relic frozen at recombination, but a record modified by billions of years of cosmic evolution and by the observer's particular vantage point. The limits of late-time explanations thus sharpen the central tension. If neither primordial physics nor local effects provide a clean account of the anomaly, the axis of evil remains suspended between explanation and coincidence. It becomes a case study in how cosmology confronts the boundary between signal, interpretation, and the unavoidable particularity of observing the universe from one place and one time. The axis of evil ultimately confronts cosmology with its own methodological limits. Unlike most areas of experimental physics, cosmology cannot repeat its experiment. There is no ensemble of universes to observe, no way to average over realizations of initial conditions. Every statistical statement about the cosmic microwave background is conditioned on a single sky, observed from a single location, at a single cosmic time. This fact is not a technical inconvenience. It is a structural constraint on what cosmology can ever know. The single sky limitation is most severe at the largest angular scales. At small scales, the cosmic microwave background provides millions of effectively independent modes. Statistical inference there is powerful, robust, and largely insensitive to rare fluctuations. At low multipoles, the situation is reversed. The quadrupole and octopole contain only a handful of degrees of freedom. Any inference drawn from them is inherently fragile, no matter how precise the instrument. This limitation is not reducible by improved technology. Even a hypothetical, perfectly noiseless, foreground-free experiment would still face cosmic variance. Cosmic variance is not uncertainty due to ignorance or instrumental imperfection. It is uncertainty due to the fact that the theoretical predictions describe a distribution of possible universes, while observation samples only one draw from that distribution. At multipole L, the fractional uncertainty due to cosmic variance scales as the inverse square root of the number of independent modes, which is 2L plus 1. For L equals 2, this implies an uncertainty comparable to the mean itself. No amount of improved calibration, longer integration time, or better foreground modeling can change this. Cosmic variance is a hard boundary on inference. The axis of evil exists precisely at this boundary. It is a geometric feature constructed from the lowest multipoles, where cosmic variance is maximal and statistical power is minimal. This places it in a category distinct from most cosmological observables. It cannot be ruled in or ruled out with the same confidence as parameters derived from thousands of modes. Recognizing this does not trivialize the anomaly. It reframes it. The question becomes not whether the axis of evil is statistically significant in some absolute sense, but what kind of evidence would be required to treat it as physically meaningful. One promising avenue lies in polarization-only analyses. Temperature anisotropies and polarization anisotropies arise from related but distinct physical processes. While temperature fluctuations are sensitive to gravitational redshifts and density perturbations, polarization is generated by Thomson scattering in the presence of local quadrupole anisotropy. As a result, polarization provides an independent probe of large-scale structure at recombination. If the axis of evil reflects primordial physics that breaks statistical isotropy, some imprint should exist in the large-scale polarization field. Crucially, polarization data are subject to different systematics than temperature data. Foreground contamination behaves differently, beam effects differ, and dipole subtraction plays a reduced role. Polarization-only analyses therefore offer a partial escape from the single sky trap. They do not provide a second universe, but they provide an independent realization of the same initial conditions filtered through a different physical observable. If a similar alignment or preferred direction were found in polarization at low multipoles, it would significantly strengthen the case for a cosmological origin. Conversely, if polarization remains consistent with isotropy as data quality improves, the space of viable primordial explanations will shrink. This does not falsify the anomaly outright, but it constrains its interpretation. It would suggest that the temperature alignment arises from effects that do not strongly couple to polarization, favoring late-time systematic or statistical explanations. Cross-correlations with large-scale structure offer another route forward. Late-time effects, such as the integrated Sachs-Wolf effect, link cosmic microwave background anisotropies to the distribution of matter at low redshift. By correlating low L temperature modes with galaxy surveys, weak lensing maps, or reconstructed gravitational potentials, one can test whether local structure contributes coherently to the observed geometry. Such cross-correlations are challenging. They require wide-area surveys with well-controlled systematics and accurate redshift information. They are also limited by cosmic variance, since both the cosmic microwave background and large-scale structure are sampling the same underlying modes. Nevertheless, consistency or inconsistency between these observables can help discriminate between primordial and late-time explanations. Future large-scale structure surveys will improve these tests. Deeper and wider galaxy maps, combined with improved modelling of bias and evolution, will sharpen constraints on late-time contributions to low-L anisotropy. While they are unlikely to resolve the axis of evil on their own, they can limit the role of local structure more tightly than is currently possible. Next-generation cosmic microwave background missions will also play a role, though their impact will be subtle. Missions designed primarily for small-scale polarization and primordial gravitational wave searches will not dramatically reduce cosmic variance at low multipoles. However, they can improve control of systematics, provide cleaner polarization measurements, and enable more stringent null tests. Improved measurements of large-scale E-mode polarization are particularly important. While temperature data are already close to the cosmic variance limit, polarization at low LL remains noise-dominated. As this improves, polarization will increasingly serve as the decisive arbiter of large-scale isotropy. The question of what would falsify the axis of evil is therefore more nuanced than it may seem. One cannot falsify it by acquiring more temperature data alone, nor can one falsify it by arguing that its p-value exceeds some threshold. Falsification would require demonstrating that the observed geometry is inconsistent with all plausible physical mechanisms that could produce it. This could take several forms. A robust detection of isotropy in polarization incompatible with temperature-based alignments would undermine primordial explanations. A clear association between low L temperature features and late-time structure would favor local explanations. Alternatively, demonstrating that similar geometric anomalies arise generically in simulations once a posteriori selection is properly accounted for would weaken claims of significance. Whether anomalies such as the axis of evil demand new physics remains an open question. From a conservative perspective, the standard cosmological model continues to explain the vast majority of observations with extraordinary precision. Introducing new physics to account for a subtle, low-significance feature risks overfitting a single realization. From a more exploratory perspective, the persistence of multiple large-scale anomalies across independent datasets invites caution but not complacency. Cosmology has learned repeatedly that assumptions once regarded as sacrosanct can be incomplete. The challenge is to distinguish genuine cracks in the model from the inevitable quirks of finite statistics. In this sense, the axis of evil functions less as a problem to be solved and more as an epistemic stress test. It probes how cosmology reasons under extreme data scarcity. It exposes the tension between probabilistic prediction and singular observation. It forces careful reflection on how significance is defined, how anomalies are identified, and how theoretical priors shape interpretation. The ultimate legacy of the axis of evil may not be a revised cosmological model or a new fundamental field. It may instead be methodological. It reminds us that the universe does not owe us clean answers at every scale. At the largest angular scales, where the imprint of the earliest moments intersects with the limits of observation, ambiguity is not a failure of science, but an intrinsic feature of the problem. Whether future data will clarify the origin of the alignment or simply sharpen the contours of uncertainty, the axis of evil will remain a reference point. It marks the boundary where cosmology transitions from parameter estimation to philosophical inference. In doing so, it reveals not only something about the universe, but something about how knowledge itself is constructed when the sample size is 1.